If you remember, last time we started with problems on streamlines and pathlines, okay? And we have considered in the first problem the case of a steady flow. Now we will see that for the case of a transient flow, what will happen is that the streamlines and pathlines will be different, and we'll see this by graphical interpretation and from equations. Okay. So we have in the following problem, water. Do you want me to zoom the screen?
Yes, please.
Okay. So water is flowing from the oscillating slit shown in the figure, producing a velocity field given by the following equation: V equals to U0 sine omega t minus y over V0. This is along I. And along J, you have plus V0J, where U0, V0, and W are constants. So as you can see, along vertical direction, the velocity is constant, while along I, it's sinusoidal with time, okay? And it will depend on the location you are and the time. So it's function of time and function of position y. Now, what we want to do is we want to first, they told us also that the y component remain constant, while for the x component of velocity at y equal to 0 coincides with the velocity of the oscillating sprinkler head, where u equal u0 sine omega t at y equal to 0. So they gave us these boundary conditions on the flow, and we want to determine first the streamline that passes through the origin at t equals 0 and at t equal pi over 2w. Okay, so whenever you have a non-steady flow and you want to determine a streamline, they should give you the time and location, because for each point you can define a streamline passing by this point. And since it's unsteady, so at each time t, we'll have a new streamline that will pass by this point. Okay. So for example, here they are interested in point O, which is the origin. So the origin is characterized, O is characterized by x equals 0 and also y equals 0. Okay. And I want to determine the different streamlines passing by O at different times. Okay. So first, let us go back to the definition of the streamline. We said that the streamline is a line where the velocity vectors are tangent to it. From this definition, we can say that for the streamline, dy by dx is equal to v over u. And v is the velocity component along y, and u is the velocity component along x. So here in this problem, we have the component along y is v0, and the component along x is u0 sine omega t minus y over v0. So if we replace in this relation, we come up with the following result. Okay. Now, what we should do here, we should do separation of variables. Okay. So since you have here a function of y, you should take it from y side. So you take it to this level, and you have times v0 dx. Okay. And now you will integrate both sides. So you have from one side, you have u0 times sine omega. And please pay attention, t here is a parameter. So when you integrate for a streamline, t is a parameter that can take any value. Okay. Now, when you integrate, you consider t as a constant, and you integrate from one side with respect to y, and from the other side with respect to x. So you have this after doing separation of variable, you have this. So now you will integrate this relation. This is a function of y, and it's a complex function. Okay, your function is, you can call this function u. So this is u of y. Okay, you know that in order to integrate a function, you need to have with it u prime. So if you have u prime times u, then the integral can be equal to the integral of the common function. And here, what you have is u prime. U is this function. So here you have sine of u. Okay, to be able to say that the integral of sine, it's cosine, you should have, before you sine u, you should have u prime. Okay, what is u prime here? This is your function. This is your function. You should derive with respect to y. Your variable is y. If you derive with respect to y, the derivative is minus w times u0. Sorry, minus w times minus w over v0. Okay, and you know that this is a constant. Because it's a constant, okay, I want to appear this term mathematically without changing anything in my equation. So to appear u prime, what I will do, I will multiply sine u by minus w v0, and then I will divide by minus w v0. And this way, I don't change anything since I'm multiplying and dividing by a constant. Okay. Now, this part is, I consider it as u prime. So this is u prime. So I just still have to consider 1 over minus w v0. If you want, since it's over v0, I will take v0 to the upper side. So it's, I should multiply, when I integrate, I should multiply by minus v0 over w. And also don't forget that since I have here also, I have a constant u0 multiplying my function. So also this, when I integrate this constant, I should keep it. So it's, the integral will give me u0 v0 over minus w times, what is the integral of sine u times u prime? It's minus cosine u. So minus cosine u. So as you can see, minus and minus will cancel out. And I get that the integral of this function is u0 v0 over w times cosine u. And this is what we have here. Okay. Do you have any problem with the integral procedure? Okay. So now I am done with the integration of the first side. From the other side, it's much simpler. From the other side, I have v0 dx. So integral with respect to x is v0 x plus constant. Okay. So now this is my the equation of a streamline. Now, in particular, I am interested into the streamline passing through the origin, so characterized by x equals 0 and y equals 0. First, for time t equal to 0. So all I have to do is to replace here by 0, 0, and the first time for t equals 0, I will get the following. I will get cosine of 0, and I know that cosine of 0 is 1. So my first relation, my first equation will be that the constant c is equal to u0 v0 over w. Okay, so for to determine the streamline passing through the origin at t equals 0, the equation will be given by just replacing t by 0 and getting the value of my constant. This will give me the equation of my streamline. Okay, so now the general equation of the streamline will be just I replace t by 0 and I replace the constant t by its value, the value I got, which is u0 v0 over w. This will give me the first streamline required, and as you can see, the streamline is y function of x. Okay, now the second streamline, so as you can see, for the first streamline, it's a straight line. Okay, because I have y, so here when I consider when I consider here for the first streamline the equation, okay, I will replace y by 0 and x by 0 for the first time to get the constant c. Okay, once I get constant c and replace back in my relation, I can get the value of my equation. This is my equation for the first streamline. So for the first streamline at t equal to 0, I get the following equation. Okay, and as you can see, this is like it contains a cosine function. So I will have like an oscillation when I represent my streamline. Now, for t equal to pi over 2 omega, I will repeat the same procedure. In order to find the streamline passing by the origin at t equal to pi over 2 omega, first I will say to get the constant c, what is my constant c? I will replace t by, first, since my time of interest is now pi over 2 omega, I will replace t by its value. And now to get the corresponding constant, I know that I need the streamline passing by the origin. So also here I will replace x by 0 and y by 0. Okay, what do I get? I have here cosine w times pi omega times pi over 2 omega. So I get omega will be simplified. So I get cosine pi over 2. And I know that cosine pi over 2 is 0. Okay, so what do I get? I get then that my constant is equal to 0 for this case. And therefore, to get my streamline equation, all I have to do is just to replace t by its value to pi over 2 omega and my constant by 0. I get the following equation. So as you can see, the equation is varying with time. At each time t, I have a new equation for the streamline passing by the origin. Okay, and I can plot it. I can plot it for different times. So let us see the plot together. So this is the result. Okay, if you plot the streamline at t equals 0, you get the following line. And if you plot it at another time, you'll get another oscillating line. Okay, and if you consider streamlines at different points, so here as you can see in this figure, I'm considering streamlines not only passing by the origin. So at a certain time t, if I take a picture of smoke, I will visualize this for a certain time. Okay, any question how to get the streamlines equations? Okay, so now we are done with the first question. The second question is to determine now the path line of the particle that was at the origin at t equals 0 and at t equal to pi over 2. So now we want to find the path line. Okay, and in order to find the path line, we go back to the equation. What is the concept of the path line? Is to track the particle with time. This means that we'll use the concept that u component of velocity is dx by dt and v component is dy by dt. And we will use the boundary condition given that we are interested first for the path line for the particle which was located at the origin at t equals 0, and the other path line that we want to determine is the path line of the particle that was located at the origin at t equal to pi over 2. Okay? So to start with the first boundary condition, as usual, we start by writing the equation, okay, which is that for first u is equal to dx by dt, okay. So now if I write the expression, if I replace u by its value, so I have u given function of time, okay. So this is the expression of u. U is given function of time and function of y. Please pay attention here. Here it's very important to pay attention because y here is a function of time. When I talk about path line, both x and y are function of time. So I cannot, like in the streamline, when I integrate with respect to t, I cannot consider y as a constant. In the streamline, when I integrate with respect to x or y, t is a parameter. I can consider it as a constant. And for each value of t, I can determine a certain streamline. Okay? On the other hand, because as I told you before, if you remember last time, when we deal with a flow field, we deal with y, x, and t as independent variables. However, when we deal with a path line, then we consider the motion of the particle with time. So both x and y will be function of time. This is the difference between the Lagrangian approach and the Eulerian approach. Okay, so when you move with the particle, you should consider that both x and y are function of time. When you deal with the flow field, you can consider that I have three independent parameters, x, y, and t. So for the streamline, when you integrate with respect to y or x, t is a parameter and you can consider it as constant. While when you find the path line and you have y in your expression, you cannot say that y is a constant. I deal with it as a constant. Okay? So what should I do then? How can I deal with this y? Okay? To be able to deal with y, first, what we will do here, okay, we have that in the problem given, okay, they told us first which point to deal with. So we wrote first our equation, okay. We wrote that, sorry, it's not here. Just let me show you the equation with time. Okay, so I have that the first equation to use is the following one. I don't know, maybe it's written somewhere. I'm not able to find it. I will write it for you. You have that dx by dt, dx over dt, okay, is equal to the u component, which is u0 times the sine omega times t minus y over v0, okay. And you have also that dy by dt, dy by dt is equal to v0, okay. Now what you can do here, first you can start with the second equation, because for the second equation the integral is pretty simple. You have dy by dt equal to a constant, so you can deduce that from this relation that y is equal to v0 times t. Okay, y is equal to v0 times t plus a constant. In this problem, because they specified the point at which the point of interest, okay, the point of interest here is the origin. So we will replace after, in order to determine our constants, we will replace by at t equals 0, the value of x is 0 and the value of y is 0. Okay, so from here you can see that y is function of time, and you got this function. Okay, now you should remember that when I deal with y here, I should know what is y function of time. So I should replace y by its value in this equation before integrating here, because x is expressed function of y and time, and I cannot integrate this function by considering y as constant, since y is also function of time. So this is why I should have done this step first to get the expression of y function of time. Now I will be ready to replace back in my equation. Okay, so now if you replace the expression of y in this expression, you will get that dx by dt is equal to u0 times sine omega, okay, times, so if I will call this constant, if you want, c1. I will call this constant c1. And if I replace in this relation, I have sine omega times t minus, now, if I do y over v0, I will get v0t over v0, which will give me first t, okay, plus c1 over v0. Okay, so what do you deduce now? T and t minus t will cancel out. So I will get the following. I will get that dx by dt, the general form of it, dx by dt is a constant. So when I integrate, okay, when I integrate, I can consider that the constant is u0 times sine omega times c1 over v0. Okay, and plus when I integrate with respect to time, then what will be the expression of x? I will have that x is u0. So when you integrate this relation, since this is a constant, so this is a constant. Okay, just guys here, because we have minus y over v0, this is minus c1. Okay, minus c1 over v0. So you get here, if you know that sine minus alpha is equal to minus sine alpha. Okay, so I will put here before it minus. So now when you integrate x with respect to time, you'll get the following. You will get that x is equal to u0 sine c1 omega over v0 times t plus a certain constant, and here you have, of course, c1, plus a certain constant c2. Okay, and this is the relations I got here. This is the same relation we got. Okay, so now you obtained the equation of y function of time and the equation of x function of time, and you are ready now to find the path line that they asked you for. What they asked you for, first they want the path line of the particle that was at the origin at t equals 0. Okay, so this condition will give you what is c1 and what is c2. So first you say the particle that was at the origin at t equals 0, I can say that for t equals 0, y is equal to 0. If you replace an equation of y, this will give you that C1 is 0. So this corresponds to C1 equals to 0. And now you replace C1 in x also, so sine of 0 will give you 0. So you have that for the origin x is 0, 0 is equal to C2. So for the first path line, you get that C1 and C2 are both equal to 0. So if C1 and C2 are both 0, what will be the corresponding equations? You will get x equals to 0 and y equals to V0t, which is what? Which is the vertical, this path line is a straight line coincident with the y-axis. So you can say that the path line passing by the origin at t equals 0 is a straight vertical line. Okay? Any question on how we found these relations? The relation of x function of time and y function of time? Okay. So now we are done with the first path line. The second path line they asked about is the path line for the particle passing by the origin, but now at t equal to pi over 2. So now we will repeat exactly the same procedure to get C1 and C2, okay? We have seen that y equation is V0t plus C1. So now to get the value of C1, we apply the condition that at t equal to pi over 2, the particle is passing by the origin, which corresponds to a value of 0 for y. So 0 equals to V0 pi over 2 plus C1. So the value of C1 will be minus V0 times pi over 2. Okay. Now, to get your constant C2, you will replace C1 by its expression in X formula. So in X formula, if I replace C1 by its value, I get the following. X is equal to minus U0 times sine of, I have C1 is minus V0 times pi over 2. Okay. And I have times omega V0. So I have here times omega over V0. As you can see, V0 will be simplified. V0 will be simplified. And I have here times t, okay, plus constant C2. Now, for this equation, to get C2, I want to apply the condition that for t equal to pi over 2, what will happen? So if I replace t, the expression of t by pi over 2, I can get the corresponding value of C2. So at t equal pi over 2 and x equals 0, by replacing here, I will get, sorry, t here, phi, there is a typing error here. He pi over 2 omega, phi omega naught. Okay, so I just have to replace t by pi over 2 omega. So this will simplify things لأنه الأوميجا and omega will cancel out. Okay, so if you replace the value of t by 2 pi over omega, you can get your constant C2. Okay, and then having C1 and C2, you can end up with the equation of x and the equation of y. And if you look at your equations of x and y at t equal to pi over 2 omega, you will deduce also that x is linear with time and y is linear with time. And if you want to draw the path line in this case, you know what should you do? How can I find the path line I should eliminate t between the two relations. If you compare the two relations here, you have t minus pi over 2 omega in this expression, and you have t minus pi over 2 omega in this expression. So to eliminate t, you just have to divide equation. So if this is 2, this is 1, you just have to divide 2 over 1. So if you do 2 over 1, you get the following. 2 over 1 will give me that y over x is equal to v0 over u0. So what can you deduce? You can deduce that at t equal to pi over 2 omega, I have my path line will be a straight line, and the slope of the straight line is v0 over u0. Okay, and also you can demonstrate that for any time t, the x and the relation, the path line will be a straight line. You know why? Because look, if you look at this expression, y is equal to v0 t. Okay, so from this relation, you can replace t by what? T is equal to y over v0. Okay, so if we replace t by its expression here, we get the following relation, that x is equal to minus u0 times sine c1 omega over v0. And of course, the constant value will depend on the point you are considering. So you need to know which point I am interested in to get c1 and c2 by replacing by x and y of this point. So it's x times minus u0 sine c1 omega over 2 and plus c2. Sorry, we replace t by its value. T is y over v0 plus t2. So as you can see, for any time t, the relation between x and y is a linear relation. Okay, this is why if you remember last time when we considered the graphs, we have seen that the streamlines are oscillating. However, path lines are straight lines. And we have demonstrated together that if I follow any particle over time, it will move through a straight line. Now, this straight line can be of can be in this side or this side. So it can have a positive slope or negative slope, depending on what? It will depend on C1 and C2, and the point I am interested in. Okay, because for each path line is defined by the location of the particle that I am considering at a certain time. So for example, when we considered the path line passing by origin at t equals 0, okay, we got